All right, good morning. Yeah, okay. So today I'm going to have you guys identify which groups each of these belong to, and then determine if it's going to be an orthopara and identify those positions. So I'm going to do the first one, and then you guys can see what I'm talking about. So this nitro group here, if we look back at our table, which we will go over before we actually start these, this is in group 6. A CH3 here would be from group 3. It means the group 3 is a higher priority group. Group 3 is an orthopara director. So relative to this CH3, the orthopara positions are these 3 here. So go through the next 5 of them, identify which group each of the 2 constituents belong to, identify if they're orthopara directors, and then highlight which positions that would be. If a position is blocked, like the orthopara positions to this OH, this mouthhold is blocking one of the ortho positions, don't label that one. All right, I'll give you guys about 5 minutes, and then we will talk through these together.
Nerd.
I'm a nerd.
Little baby nod. Babies. Little baby nerd. Yeah.
All right, I'm actually gonna start by just redrawing our table. We're gonna have two different groups. We have deactivators and activators. Deactivators are all going to be electron withdrawing groups. Activators are electron donating groups. Dying. Our activators are all orthopara-directors. And one group of our deactivators is also in this category. The rest of them are going to be our meta-directors. So let's start out with group one. This is our strong activators. It's going to be great things like an OH or an ether. As well as things like an amine, which can either have hydrogens or R groups on them. Same with the oxygen here. Our group two is going to be similar to our group one, except we are going to have something that is slightly drawing electrons away from our oxygen. Or nitrogen. So an ester, where the oxygen is attached to our ring, these two lone pairs can either donate into our ring or donate into our carbonyl here. So unlike up here where they're entirely donating into our ring, it's somewhat split for this case. Same thing with an amide. Our group three is our weak activators. Could be things like carbon, toluene, ethylene, bigger groups, stuff like that. Our weak deactivators, so group four, this is going to be halogens. We are still in the orthopara-director category. Our group five is where we start having meta-directors. These are moderate deactivators. And this is going to be anything with the carbonyl on it, directly attached to the ring. So ketone, aldehyde, carboxylic acid, ester, where the ester is attached, or the carbonyl is attached to the ring, as opposed to this ester up here where the oxygen is attached to the ring. Amide, nitrile, so C triple bond N, and sulfate, which has essentially two carbonyls, one to either side of this sulfur group here. Our group five, which is our really strong deactivators, going to be things like a nitro group. Could also write this as NO2. A quaternary amine, so nitrogen with 4 bonds to it, a positive charge, and CF3 is going to have a lot of induction to it. Okay, so let's take a look back at this chart here. Our OH was from group 1. Our toluene here is from group 3. Group 1 outranks group 3. It's an orthopara director. We need to add to the orthopara position, so it would be this one here, and then this last one from toluene is going to be blocked. For our next problem, this is a group 5. This is a group 6. 5 is meta directing. One of the meta positions is blocked by the CF3, which means it's going to add to this position. All right, tertiary amine would be group 1. Quaternary amine would be group 6. Means it'll add orthopara to this group 1, all of which should be open. We have a group 2 and a group 5. So we'll go orthopara to the group 2, which would be these 2 positions here. And for our last one, we have a group 1 and a group 2. So we'll prioritize the group 1. It's an orthopara director. The pair is blocked. So we can add to these 2 ortho positions. All right, let's start getting into reactions. I'm going to review the 2 we did on Monday and then just kind of push forward with the rest of them. They all follow a very similar pattern for their mechanism. It's just going to change how we make that electrophile. So let's take benzaldehyde. This is a meta director. It's from group 5. We throw in Br2 and FeBr3. This will make a complex that looks like this. There's a question in the chat. Yeah, I would memorize this table. It will not be under exam. Okay, so meta director here. This is going to attack this bromine, kick out the electrons. I'm using this marker. It is going to break our aromaticity. We're going to add bromine to the meta position. And then from here, our FeBr4, which is a Lewis base, can pick up our proton, re-aromatize, to give us our final product. All right, chlorination. We can do the same concept with a Cl. It's almost the exact same reaction. So let's take a group 1. We'll throw phenol on there. There's a question in the chat. This is the, yeah, so this is the AS. We'll actually cover NAS at the end of class. There's only one reaction. These are all electrophilic aromatic substitutions. Okay, so chlorination. We have a group 1 here. It's an ortho-para director, so it can add to either of these positions. There's 2 different products we can get. Either where our CL adds ortho, or where our CL adds para. This works by an identical mechanism. We've just swapped out aluminum for iron for aluminum. I'll show how to make the para product. So our para position can come in, do an attack on our chlorine. From here, our AlCl4 picks up the proton, re-aromatizes, and we can make our product. We are going to learn 4 more of these reactions today. They're all going to use this same type of mechanism where you're going to attack some sort of electrophile, pull off a proton, re-aromatize. The only thing that's going to really change is the complex we make, how we make it, that kind of a thing. So let's start with sulfonations. Let's put a meta director on there. So this nitrile group. If I add in something called fuming H2SO4, which is literally just boiling H2SO4. So boiling sulfuric acid. What happens is we have 2 sulfuric acid molecules that interact with each other. One of them is going to donate a proton to the other one. So I'm going to pick up a proton here. We'll make water. Our other oxygen on our H2SO4 can kick out this water, and we're going to make an electrophile. Going to look like this. We have a meta director. And from this point, we're going to do the exact same reaction we were doing. So a nitrile is a meta director. Our ring can attack. This electrophile. We'll lose our aromaticity. add a sulfonyl group. From here, we made HSO4 minus in the first step. So this will grab our proton, re-aromatize. And we can get sulfonation. So exact same concept. We just switched out how we made our electrophile. And we're able to do a sulfonation reaction. All right, so adding in a nitro group. Let's take toluene. This is a group 3. Going to be an ortho-para director. If we throw in nitric acid, which is HNO3, as well as H2SO4 again. In this case, we're going to nitrosylate. And I'm going to show you what the products are first, and then we're going to go through how to do it. They're going to be adding NO2. This is an ortho-para director, so you can either add to an ortho or a para position. This is going to work by a similar mechanism. We're going to take our nitric acid, which looks like this, and mix it in with H2SO4. H2SO4. Sulfuric acid is the better acid. So it's going to donate a proton to our nitric acid here. We'll make water again. Our oxygen with the negative on it can kick it out. And we're going to make our electrophile. I'll do the ortho for this one. So our aromatic ring can do an attack of this. We are going to make we'll kick the electrons up to one of these oxygens. A nitro group here. In the first step, we made a base, which was HSO4 minus. It'll grab the proton and re-aromatize. Someone asked, what is this mechanism called? This is EAS. This one specifically is nitrosylation. The other one was sulfonation, and you have bromination and chlorination. Just whatever you're adding with Y-lation at the end. Okay. Our next one is going to be an alkylation. So we're adding carbons to this. This looks a lot like the chlorination mechanism. If we take, let's do this with something interesting. Put bromines on here. Okay. We have a group 1. We have 2 group 4s. Our group 1 is an ortho para director. The 2 pairs are blocked. So that leaves this one position, or 2 orthos are blocked, it leaves the 1 para position at the bottom. If I add in an alkyl halide with AlCl3 here, this is going to make a really similar complex to what we were making with just Cl2. So we're going to get something that looks like this. We want to compare this to our chlorine complex. We've got these 4 chlorines with an aluminum in the middle and then a carbon chain. You had 4 chlorines, aluminum in the middle with a chlorine on the end. So this alkyl group has essentially replaced that chlorine. This is actually going to fall apart. We're going to end up breaking this bond here, and we're going to get AlCl4 and the carbocation. So from here, our para position can do an attack on our carbocation. Make a new carbocation in a ring. AlCl4 can pull off our proton to aromatize. And we can alkylate our ring. So this lets us add any sort of carbon group we want to the ring. There's going to be a problem with it that I will talk about in a second. Okay, this step here is going to be a bit of a pain. And the reason behind that is this is an actual carbocation, which means that this can do rearrangements. So let's take the same molecule. wrote in something. That looks like this here. We can make a complex. Our complex can fall apart. And we'll make a carbocation. This is a primary carbocation next to a tertiary center. So it's going to rearrange. We're going to have a hydride shift happen. And end up with that carbocation on a tertiary. From here, we're doing the same reactions we normally would. So we can attack. Our AlCl4 can pull off that proton. And lets us alkylate. So this reaction is alkylation, or EAS alkylation. All right, so this doesn't really give us the product we wanted, right? So if I took, to rewrite it out, so this wasn't really what we're looking for. We ended up rearranging, we got a different product. So the question is, how do we get from here to what we actually wanted? To that non-rearranged product. The way we're going to do this is going to be through two different reactions. To avoid the rearrangement, we're going to do what's called an acylation. Which is very similar. We're just going to have our carbonyl now. This is going to let us generate the product we want. With an acyl group on it. And then we're going to add in a reducing agent, which I'm going to talk a lot more about on Friday. So zinc, mercury, and HCl will allow us to reduce this. Get rid of that carbonyl and give us the product we want. Our acylation mechanism is basically the same mechanism. We're just having an extra carbonyl on there. I'm going to do this for something different so I don't have to. Let's put an ether on here. Okay, so we have an ether, that's an ortho paradirector. We'd end up with these two products here. The way it's going to work is the same way that alkylation works. We'll make a complex, our complex will fall apart. We're going to generate a carbocation, which our ring can attack. We'll re-aromatize with AlCl4. Oops, take a minute to go to this one. To get our final product. All right, so let's take a look at all of our EAS mechanisms. I put a nitro group on there, so it's a meta director. We can brominate, so throwing in Br2 and FeBr3 lets us add a Br. We can do a chlorination, so Cl2 AlCl3. We can sulfonate with fuming H2SO4. We can nitrosylate with HNO3, H2SO4. We can add carbons with our two different reactions. So the first one is alkylation. And we could also acylate with the acyl version of this. All right, so these are the EAS reactions. There is also nucleophilic aromatic substitution. Someone asked if the alkylation will also work with a bromine complex. Yeah, you could put a Br here and FeBr3 and it would also work. It's just the same thing. I think the book only does the AlCl3 version, but there's no reason you couldn't have either. All right, the nucleophilic substitution is a lot simpler. There's only really one reaction with them. This is NAS. And it's essentially an SN2. It's gonna have some requirements to it. One requirement is you're gonna need some sort of resonance contributor. So if I just tried to do a normal one, which would be throwing in NaOH and heat H0 plus, this is gonna give us no reaction. You're gonna need something in either your ortho or your para position in order to do this. And it pretty much has to be a nitro group. You might be able to do it with a sulfonation, but the one that is most used is gonna be this here. So what happens when we throw in these exact same reagents, we're gonna have our OH try to do an SN2 at our bromine position. So it'll come in, attack here. These electrons are gonna get kicked all the way down to this nitrogen. And we're gonna form an intermediate, which is why we need the nitro group on it. Our intermediate will look like this. And then from here, we can have our electrons come back up, kick out our bromine. To give us our substitution product. All right, so that's NAS. I kind of draw a couple of different examples of it. When it works, when it doesn't. with a nitro in the para position, it works fine. OH can replace BR if it's in the ortho position. This will also work. Gonna put quotations for the same thing. If I try to do this where it's meta, when my OH attacks, it's never going to be resonance stabilized. So if I attack here, my electrons could shift down over. I don't have a way to get to this position here. They're just going to keep shifting around this ring and they're going to be stuck. So it doesn't work when it's in the meta position. You don't have that stabilizing effect. These are all dead. The markers. So when it's meta, it's also going to lead to no reaction. And then the same thing if it's just straight, there's no substituents on it, will also give you no reaction. So it has to have it either ortho or para to be able to contribute to any sort of resonance and for the reaction to actually work. All right, that is all I'm going to cover for today. On Friday, we'll do some chapter 22 reactions that are very similar. And then probably talk about some synthesis problems.